Hello. The purpose of this lab was to observe the motion of a falling object and use some of these observations to predict the motion feature of this object. We did this by constructing models using Newton's second law and its derivative. One of our models used weight force as the only force, and the other used both weight and drag force. My computational model using both weight and drag force was closer to my observation than my model using weight as the only force. To get started, I uploaded my video into Tracker. I was able to set my coordinate system with the origin being at the center of the ball before it is dropped. I set my length scale to my friend's height from his shoulder to his knees, and as well as I marked the point of mass of the ball at each time frame. It's important to see that as the time frames got later, the position of the ball was quite hard to see as it was blurry. So I had to use my best estimate, as well as the coordinate system is tilted at an angle. This is because the ball falls at an angle to my camera, as well as it is falling in the negative y direction. From the point of mass markers, we are able to get information on position and time, which we can put into a graph. We are able to see the position of the object in the y direction as a function of time, shown by the blue boxes in the plot made. It is important to note that the time duration of our video is 0.435 seconds. At the beginning of the video, our ball is located at the position 0, 0, 0, and it has a 0 velocity. Now, to apply Newton's second law to predict and describe our motion, we see that there is a change in velocity, which means that there is an F net. But what is F net? We don't know. So at first, we're going to assume that F net is only the weight force, which is negative mg in the direction of y. So now we can start our script using this first assumption. Our initialization that the ball is originally at 0, 0, 0 and it has a 0 velocity is put in, as well as the ball's mass. We have our delta t, which is the delta t of the frames in our tracker. We edit the fact that there is a weight force acting on the ball, and this is then added into Newton's second law equation for velocity, which then affects the equation for position. We can then get a graph of this and see that our model for this one and our observation is very different, and it's not good enough. So we're going to have to find a different assumption to make. Now for our second assumption. Let's say that there is a drag force acting with this force of weight. Maybe we can get a better observation and model correlation. The only change we really make to the script is that we're adding the drag force, which is proportional to the magnitude of velocity squared. To find the proportionality constant, it's just a guess and check method to find. Mine was 0.004 Newton second per meter. When I find this, I get a graph, and I see that this is highly accurate, and it's a lot better than my previous graph. However, there are still distortions. Maybe this is because the camera was at an angle, and we can improve this by making it straight or finding a better way to find the drag force. To the what does it mean question, which of these models gives us a better prediction of terminal velocity? Terminal velocity is when the drag force and the weight force are equal and F net is 0. So that means the slope of the velocity is going to go to 0, which this doesn't happen in the first one. But in the second one, with both drag and weight force, we see that this does begin to happen, so this would be a better predictor. Now to the what if question. This is asking if the ball is thrown down with an initial velocity, how will the terminal velocity be different or the same? So we see that if we run this program with an initial velocity of -9, which would be happening if we threw it down, that we would get a model in which our drag force is actually going to be greater than our weight force. However, we see that, and it's decelerating when it starts. However, that we see that it is going to reach a terminal velocity. This just happens a little sooner. Thank you.